Hello everyone. In this video we're starting with example 3.2.7. In part A we're asked to transform the following augmented matrix into row echelon form using elementary row operations, and we want to give the system of linear equations that corresponds to each augmented matrix. First, let's recall elementary row operations. There are three of them. We can interchange two rows, row I and row j. We can multiply a row by a non-zero constant, k times row I, where k is not equal to 0, and we can add a multiple of a row to another row. So row I plus k times row j. So on the left here we have the first augmented matrix, the one that's given to us. On the right we have the corresponding linear system. Now this augmented matrix that's given to us is not in row echelon form. We know that an augmented matrix of this size must have that at least these three entries are 0 in order for it to be in row echelon form. And so we need to make decisions about which elementary row operations we can use in order to transform this augmented matrix into one that is in row echelon form. Now first notice that there is a 0 here. The first entry of the first row is 0. And so if I interchange row 1 and row 3, I will have moved that 0 into the bottom left corner, which is where I want to have a 0. And so that will be my first elementary row operation here. I will interchange row 1 and row 3. That will give me a new matrix. The first row is now the old third row. So I have 1 minus 2 minus 1, 4. The second row remains unchanged, 2, 1, 8, 3. And the third row is now the old first row, so 0, 2, 1, 4. Now I have a 0 in the bottom left corner. That's good. I'm making progress. Now what is the corresponding linear system? Well, from the first row of the augmented matrix, I get the equation 1 times x minus 2 times y minus 1 times z equals 4. From the second row, I get the equation 2 times x plus 1 times y plus 8 times z equals 3. From the third equation, I get 0 times x plus 2 times y plus z equals 4. What happened on the system level? Well, I interchanged two equations. And so interchanging two rows in the augmented matrix is equivalent to interchanging two equations in the corresponding linear system. If I interchange two equations in the linear system, I'm not changing the solution set of the linear system. The next entry that I would like to work on is this 2. If this 2 was a 0, we would be one step closer to having a matrix in row echelon form. Now, how can I make this 2 become a 0? Well, I can add a multiple of the first row to the second row in order to make that happen. So I'll take my row 2 and I want to add a multiple of row 1. Which multiple of row 1 should I choose? Well, row 2 minus 2 row 1 will do the trick, because 2 minus 2 times 1 is 0. So let's do that. The only row that's changing now is the second row. The first entry is 2 minus 2 times 1, which is 0, as we wanted. The second entry is 1 minus 2 times minus 2, so that's 1 plus 4, which is 5. The next entry is 8 minus 2 times minus 1, so that's 8 plus 2, which is 10. And next we have 3 minus 2 times 4, 3 minus 8, that's minus 5. There we have our new second row. The first and the third rows don't change. So we have 1 minus 2 minus 1, 4 in the first row, and 0, 2, 1, and 4 in the third row. Now, what is the corresponding linear system? Well, in the first row, we have x minus 2y minus z equals 4. In the second row, we have 5y plus 10z equals minus 5. In the third row, we have 2y plus z equals 4. That's our new corresponding linear system. Now, what happened to the linear system? Well, adding a multiple of a row to another row in an augmented matrix is equivalent to adding a multiple of an equation to another equation on the system side. And that doesn't change the solution set of the system. Now let's go back to the augmented matrix. The augmented matrix that we ended up with still isn't in row echelon form. This 2 is not a 0 yet. We need that 2 to be a 0 in order for this augmented matrix to be in row echelon form. Before taking care of that 2, I'll do the row operation 1 over 5 R2. I'll multiply every entry of the second row by 1 over 5. So I'll get 0. 1 over 5 times 5 is 1. 1 over 5 times 10 is 2. 1 over 5 times minus 5 is minus 1. That's my new second row. My first row stays the same. 1 minus 2 minus 1, 4. 0, 2, 1, 4 is my third row, which also stays the same. The corresponding linear system is x minus 2y minus z equals 4, y plus 2z equals minus 1, and 2y plus z equals 4. Now on the system side, what happened was that I multiplied the entire second equation by 1 over 5, which doesn't change the solution set of the system. Now I'm going to take care of this 2. And I'm going to use the 1 above it in order to do that. So my new row 3 will be row 3 minus 2 row 2. That will give me a 0 in that position. So in the bottom left, I have 0 minus 2 times 0. That is still 0. Next, I have 2 minus 2 times 1, which is 0. That's the 0 I've been looking for. Next, I have 1 minus 2 times 2. 1 minus 4, that's minus 3. And finally, I have 4 minus 2 times minus 1, so that's 4 plus 2, which is 6. That's my new third row. My first row stays the same, and so does my second row. And now I have the long-awaited 3 zeros in the bottom left corner that I fought hard to get. This new augmented matrix is in row echelon form. What does the corresponding linear system look like? Well, my first equation is x minus 2y minus z equals 4. Second equation is y plus 2z equals minus 1. And my third equation is minus 3z equals 6. Now this new linear system is again equivalent to the one above it, because all I've done on the system side is added a multiple of an equation to another equation, which doesn't change the solution set of the system. Now this example actually has a part B. There's my part B. I want to solve the system using back substitution. I'm going to take my new system that I've just found and solve that one using back substitution. So I have 3 equations, 1, 2, 3. I'm starting with equation 3 and I'm solving it using back substitution. So minus 3z equals 6. I can solve for z. Z will be equal to minus 2. Then I move to equation 2. y plus 2z equals minus 1. Now I know that z is equal to minus 2, so y plus 2 times minus 2 is equal to minus 1, and I can solve for y. Y minus 4 is minus 1, and so y is equal to 3. And equation 1 will allow me to solve for the remaining variable, which is x. X minus 2y minus z equals 4. Now I'll plug in the y and z I've just found. So x minus 2 times 3 minus 2 equals 4. And I have x minus 6 plus 2 equals 4. And so x is equal to 8. And so I've solved the system. The solution is x, y, z equals 8, 3, minus 2. And so what is the takeaway from this example? Well, interchanging two rows in an augmented matrix is equivalent to interchanging two equations in the corresponding linear system. In the same way, multiplying a row by a non-zero constant in an augmented matrix is equivalent to multiplying an equation by a non-zero constant in the corresponding linear system. And finally, adding a multiple of a row to another row in an augmented matrix is equivalent to adding a multiple of an equation to another equation in the corresponding linear system. And that leads us to this important proposition, proposition 3.2.2, which says that performing elementary row operations on an augmented matrix does not change the solution set of the corresponding linear system. And this fact allows us to solve linear systems the way we solved a linear system in the previous example. We will be performing elementary row operations on an augmented matrix in order to transform it into an augmented matrix in row echelon form. The linear system corresponding to that augmented matrix in row echelon form is then easy to solve using back substitution.